Welcome to The Explainer. Today, we're looking at an absolutely staggering feat of engineering, specifically focusing on the GF 12,000 drillship. No anchors, no chains. Just imagine for a second, standing on a vessel that is effectively a 6-story steel building floating out in the open ocean. Your job? Drill a well straight into the seabed. But there's a pretty massive catch. You are operating in waters that are 3,000 meters deep. That's almost 2 miles of water between your hull and the ocean floor. The sheer scale of that challenge is mind-boggling, and the very first problem you have to solve is simply staying in one place. Okay, let's dive right into this, because this is where traditional maritime logic just completely breaks down. Think about it. How do you anchor a massive, incredibly heavy drill ship in 3,000 meters of water? Imagine the absolute impossibility of dropping a physical anchor chain in an ocean that deep. I mean, the weight of the chain alone would either pull the ship under, or it would just snap under its own immense tension, long before it ever found a solid grip on the seabed. There is literally nothing practical to hold on to. So what's the answer? Well, you don't. Traditional anchors and chains are completely useless out here. Instead, these vessels rely on something called dynamic positioning, or DP. This is essentially the ultimate high-tech substitute for an anchor. It's this invisible mooring system that uses immense, continuous active power to hold the ship locked over a wellhead to within just a couple of meters. It fights wind, waves, and current without ever physically touching the seafloor. To pull off this seemingly impossible task, you need an unbelievable amount of hardware. Which brings us to Section 1, 33 megawatts of muscle. Right beneath the massive hull of the GF 12,000, mounted completely underwater, are 6 independent thrusters. And we're not talking about your average boat propellers here. These are massive Rolls-Royce thruster pods that hang below the ship, heavily engineered to operate in the harshest marine environments imaginable. To put their capability into perspective, each individual thruster pod generates 5.5 megawatts of power. To visualize that, just one single pod is roughly equivalent to the combined muscle of about 7,000 family cars. And remember, that's just one of them. So when you do the math, multiplying the number of units by the power per unit, you hit a staggering 33 megawatts of total installed thrust power. To give you a real-world comparison, 33 megawatts is enough juice to run a small town of about 20,000 to 25,000 homes. And on this vessel, all of that power is dedicated to just one single objective: holding one ship perfectly still. But as you can probably guess, raw power alone isn't enough to fight the unpredictable forces of the ocean. It's all about how that thrust is cleverly directed. That brings us to Section 2, the azimuthing advantage. Now, you might be wondering, what exactly does azimuthing mean? Put simply, it's the ability of a thruster to rotate a full 360 degrees on its vertical axis. This allows it to point its thrust in literally any horizontal direction. Think of them like massive outboard motors bolted to the bottom of the hull rather than the back of a boat. Because they can steer independently in any direction, they provide this frankly incredible level of maneuverability. Let's pause here for a second. I have a question for you, and it's actually something that most junior engineers get totally wrong when they first step aboard these ships. When a massive storm rolls in with heavy winds and currents, does the ship just naturally turn to face the wind like a weather vane? Well, reality actually busts that myth right open. The vessel typically maintains a completely fixed heading and position. It doesn't turn the hull to face the weather at all. Instead, the thrusters underneath individually rotate to whatever angle is necessary to counteract the environmental forces. A great analogy here is a shopping cart. Think of a cart with 4 independently steerable caster wheels instead of fixed rear wheels. You can push that cart sideways, diagonally, or spin it in place without ever changing the direction the basket is facing. That's exactly what these 6 azimuthing thrusters allow the drill ship to do. Having all these steerable thrusters is amazing, but they obviously need a brain to coordinate them, which brings us to Section 3, dynamic positioning in action. Actually, before we get to the computer, there's one more physical detail that massively boosts efficiency. These aren't just open propellers. They're fixed-blade propellers housed inside shrouds, or nozzles. Why do that? Because a nozzled propeller accelerates the water flow, squeezing out 20 to 30% more static thrust efficiency compared to an open propeller of the exact same power. When you're burning diesel to generate 33 megawatts, that kind of efficiency is absolutely vital. Okay, so here's how the DP control system works continuously in the background. First, a vast array of sensors on the ship measures the incoming wind, wave, and current forces. Second, the DP computer rapidly calculates exactly how much resistance is needed to counteract those specific forces. And finally, the system commands each individual thruster's azimuth angle and thrust magnitude. It's constantly summing all 6 thrust vectors, updating multiple times a second to produce the exact net force and moment required to keep the ship within a meter of its set point. Again, all without turning the massive hull. But make no mistake, the stakes with dynamic positioning are incredibly high. The sources highlight a quote from a DP operator on a similar vessel facing heavy seas who said, "If we lost one thruster, the situation could become critical. It may affect our actual positioning over the well." This is exactly why DP3 systems are designed with immense redundancy, ensuring no single failure results in a loss of position. That being said, in extreme weather, every ounce of thrust is needed. So sometimes the bridge crew will proactively command a slight heading change, manually twisting the ship to take the heaviest seas head-on, specifically to minimize motion and give the thrusters a hand in maintaining their grip. Now imagine the logistical headache of maintaining these colossal underwater machines. That leads us to Section 4, no dry dock required. The crucial point here is that taking a vessel of this size into a dry dock just to fix a thruster is highly impractical and honestly economically devastating. Plus, the thrusters themselves aren't even load-bearing for dry docking anyway, so they have to be maintained in the water. Historically, this meant highly complex operations, where divers would detach and replace the units directly in the open sea, a maintenance cycle that happens roughly every 5 to 15 years due to wear and tear. But on modern vessels like the GF 12,000, there's an even better solution. They are fully retractable. The ship features a dedicated rectangular canister and a massive rack and pinion jacking system. If a thruster fails or needs an overhaul, this system slowly and safely retracts the entire 5.5 megawatt unit straight up into the hull, completely out of the water without the ship ever having to leave its location. It's truly a cathedral of engineering. So the next time you see footage of a massive drill ship holding perfectly still in the middle of a vast churning ocean, ask yourself, what kind of invisible mathematical storm are its engines fighting down below? Because beneath that calm surface, 33 megawatts of muscle are battling the ocean every single second just to keep it absolutely stationary. Thanks for joining me on this explainer, and I really hope you leave with a whole new appreciation for what it actually takes to stand still at sea.